Okay, what is this phenomena, electromagnetic induction? See, in the early period of 19th century, there were scientists like Oersted and Ampere. They proved and they gave conclusions as well as derivations also for the fact that moving charges produces magnetic field. What is moving charges? Moving charges is nothing but current. Current is a moving charge, right? So current produces magnetic field. So later on, other scientists, they also proved the converse of this fact. That means magnetic field produce moving charges. That means magnetic field produce current. So right now you have to deal with two things. First of all, in our previous lecture or previous unit, magnetic effects of current, what we studied, that whenever there is a current, there will be magnetic field. That means magnetic field is associated with moving charge. But right now we are conversing it, and this is also true. Scientists like Joseph Henry and Faraday. Joseph Henry, I'll complete my statement first before I go to the scientist. The converse is also true. The converse is what? That this time magnetic field will be producing current. Okay. So this is what electromagnetic induction is all about. I'll explain you in detail. Joseph Henry was a scientist who was playing with a radio, I guess. So what he was doing, he was playing, or he was doing some experiment, conducting some experiments with radio, where he was having a galvanometer. You know, have you seen galvanometers in your physics lab? It's like this big shape, right? And you have two knobs over there where you make the connections. So this time both these things, both the wires were connected, and he suddenly dropped a magnet in this whole thing. This thing is placed on a table. Consider that galvanometer is here. This is galvanometer, and the wires are connected like this in an irregular, making an irregular loop, and then you drop a magnet here. He suddenly found that there is a deflection in the galvanometer needle, and it was like, wow, how did this happen? There is no source of EMF, no source of voltage or potential difference across the circuit, but still there is a deflection. He tried again, and then he saw that okay, deflection is happening every time the magnet is being passed from this circuit. So this whole experiment was done by Michael Faraday in a very good way, and now we are going to study Michael Faraday. But first, the definition of electromagnetic induction is, it is the phenomena of production of induced EMF or induced current in a loop or closed circuit. Again, it is the phenomena of production of induced EMF or induced current in a closed circuit when magnetic flux linked with it changes. The word changes is important because if your magnetic flux is not changing, there will be no induced EMF. So what do I mean by induced EMF? Just EMF is the voltage, presence of voltage, right, due to which there will be current. But induced is, it is getting produced automatically without any source. This is what word induced means. So Faraday's laws, and how these Faraday's laws were devised, there were few experiments conducted, and on the basis of the results these laws were formulated. See, first of all, consider this circuit. Again, a very simple circuit. There is this galvanometer, and they are connected. Both the ends of the galvanometer wires are connected. We have a magnet here having north pole and south pole, and first of all, what was noticed that whenever this magnet is brought closer to this loop, there was initially galvanometer has zero deflection. When the magnet was brought closer to this loop, the galvanometer gave a deflection and it came back to zero. When the magnet was taken away from the whole loop, again there was a deflection, but this time it was in the opposite direction, and again it was back to zero. See the difference. When the magnet is getting closer, whichever side the deflection is taking place, the reverse thing happens when the magnet is taken away from the loop. Okay, the sides, that means the direction which magnet is taken depends, that makes the difference of the deflection. Number two, faster we used to move magnet towards the coil, that means faster you make the movement, higher was the deflection. More the movement, faster the movement, more was the deflection. So these two experiments were used to make the laws which are called as Faraday's laws of electromagnetic induction. Note it down. What are Faraday's laws of electromagnetic induction? First of all, first law is whensoever there is a flux, whensoever there is a change in flux linked with a circuit, and induced EMF is produced in it. I write it down for you because this is very important. Whensoever there is magnetic flux, there is change in, not just magnetic flux, whensoever there is change in magnetic flux linked with a circuit. Why did I especially mention this word change? Because in this simple experiment, when magnet was here and it is taken towards the loop, or if it is taken away from the loop, nothing is changing except the fact, suppose magnet is at this distance and only 4 lines are passing through this loop. That means flux has a value of 4. Suppose when magnet is this much close, let us say the 40 number of lines is passing. So in this whole process, when magnet is brought closer to the loop or it is taken away from the loop, only thing changing in this whole apparatus is what? It is the number of magnetic lines of force which is passing through this loop, and that is why it was concluded that change in flux is responsible for the flow of current or production of current in this loop, or which was called induced current or induced EMF. So change in flux, this is the main factor which is responsible. So whensoever there is a change in flux linked with a circuit, an induced EMF, an induced EMF is produced in it, which now we have to specify till what time this induced EMF will sustain in this circuit. Will it be for permanent basis? No, it will be present in the circuit till the point the change is continuing. For example, I have the magnet here, I brought it up to this point and it stopped. What will happen? The deflection in the galvanometer needle will be till the point when the magnet is moving, because till the time it is moving, the change in flux is continuing, right? So when it is here, the flux is constant. Flux is not zero, it is constant. For example, here I said that is 40 lines are passing through this loop. So when magnet is brought at this point, 40 lines is constant, there is no change, and hence the deflection would be 0. So we have to also state that in it which lasts so long as the change in flux continues. Okay, I am trying to write fast, so please pardon my bad handwriting. I hope you won't mind. Number 2, what else? From first experiment we noticed that there is an induced EMF which is getting produced due to changing flux, and it is present in the loop only till the point when the change is there, change is consistent. If the change goes 0, that means when the magnetic flux value is a constant, then there will be no induced EMF or induced current, right? So second point will be, the second experiment was about faster you bring magnet closer or away to the coil, more will be the deflection. That means magnitude of induced EMF, magnitude of induced EMF is directly proportional to rate of change of flux linked with the coil. So magnitude of, okay, I can read it, so it is quite decipherable, you can read it, guys. So magnitude of induced EMF, what is magnitude? How much strength of induced EMF is getting produced in the loop, or how strong the current or induced current is getting produced in the loop. It will depend on the rate, how fast the magnet is being taken towards the loop or away from the loop. These are 2 Faraday's laws, right? So on the basis of 2 laws, there is another law. I know you guys must be murmuring right now ki then there is another law, that is third law, which gives the direction of induced EMF Okay, I will not include the third law in the Faraday's laws because that law was given by who? Lenz. Yes, exactly. This was Lenz law. So that we will include in the formula. According to this, suppose induced EMF is this, which is being produced, and consider this. Let initial flux passing through the loop be phi 1 and final flux is phi 2. So what is change in flux? Phi 2 minus phi 1. This is the change in flux. What is differential format or rate of change of flux upon T? Phi 2 minus phi 1 upon T is what? Rate of change of flux. For very small change in flux upon very small change in time, it would be d phi upon dt, right? So I'll just use this much part, d phi upon dt. Magnitude of induced EMF is directly proportional to rate of change of flux, that is d phi upon dt, but with a negative sign. Why with a negative sign? Because this negative sign was given by Lenz's law, according to which the direction of induced EMF was explained. Induced EMF always takes such a direction so as to oppose the cause responsible for its production. This was the underlying statement of Lenz's law. I will repeat it. Induced EMF always takes such a direction so as to oppose the cause responsible for its production. We'll explain Lenz's law again, but for now, E is proportional to minus d phi by dt. E is equal to k times minus k times d phi by dt. What is k? Constant of proportionality. But in SI system, k was equal to 1. So the basic formula we have is E is equal to minus d phi by dt. This is the mathematical form of, or the mathematical expression of Faraday's laws of electromagnetic induction.